Okay, so I think we can start. So welcome everyone. So it's a pleasure to host today's guest, Professor Yulia Sandamirskaya. So she's a full professor and head of the Research Center for Cognitive Computing in the Life Sciences in ZHAW in Wädenswil, where she leads the Neuromorphic Computing Lab. Her group develops neuromorphic and cognitive AI technologies with focus on applications such as service robotics, including elderly care. Before joining ZHAW, she was a group leader at the Institute of Neuroinformatics at UZH and ETH, and later led the applications research team within Intel's Neuromorphic Computing Lab. She's also a co-founder of Auroniq Robotics, a cognitive robotics integrator. So please join me in welcoming Professor Sandamirskaya.
Thanks so much for the kind introduction, and thanks a lot for the invitation. My pleasure to be here. And tell you about neuromorphic computing. Maybe to set the flight height in the right way, how many of you already know neuromorphic computing? Oh, okay, very good. Event-based vision, maybe? Event-based cameras, dynamic vision sensors, a few more. All right, that's good, because we'll go through the basics. I will, however, start with the service robots, just to motivate the heavy, exotic stuff that will follow at some point. So we, Wädenswil is a University of Applied Sciences, so we are interested in building technology that can work and serve people in the near future. And so there's this opinion existing that we really need robots that are capable to assist people in all kinds of jobs. People are sometimes afraid that robots will take away jobs, but it's not quite true. Many people are engaged in the jobs that are physically damaging or mentally straining. Repetitive, boring. You have to do these jobs in some ungodly hours, 3-4 shifts at night. The society is aging. On the one hand side, old people need some care. On the other hand side, there's less and less workforce out there. And there are a lot of sectors where actually workforce is lacking. And the young people don't want to do many of those jobs, which are the basis of our society. And those jobs are not yet automated for different reasons. And one of them is that the robots are not quite as capable as humans yet. Okay, so now we are in this year or decade of robotics, right? I'm pretty sure in this room every single person has seen the video from the Chinese New Year's festival. So the question is, how much closer do we get to robots capable to take over those jobs or assist people in those jobs if we look at these dancing robots? So one could ask ourselves, how much different are those dancing robots from the automation that we already have had since the 50s, right? In the automotive factory, it's also a beautiful dance, like super synchronous, very nice, fast, precise. You could say, could be a little discussion, how much different is what we see in those synchronized dances. And if you've seen one of those robots closer, and that's, I think, maybe from Iris conference or from one of the exhibitions, like watch the man in the background, right? So that's the typical, no? The robots do their choreography and someone, hey guys, keep away, right? So the first question that comes to my mind, and we're working on robots for care, elderly care, how safe are these guys? So are they safe? Can they work next to humans? And you can answer, well, look, we have robots that can do stuff next to humans, right? Like, can be very elegant. And you can even put them in humans' homes and they do stuff there. And they can solve very sophisticated tasks, like cleaning the toilet. That's the Loki robot, I guess, well known here. That's the spin-off from ETH. Now, what do all these robots have in common? They're teleoperated, not autonomous. That's, of course, the first step. So the human is behind. You don't really save the workforce. I just visited the airport yesterday, and they have some autonomous buses driving around for internal use, and they have remote drivers actually too. And it seems to be a pretty boring job to sit there and monitor that this autonomous thing does the right thing. Do these robots bring us closer to having that autonomy? Of course, some people believe that yes. Why? Because they had this idea that let's replace all those robotic theories that you guys probably study and know, like algorithms, software, with one big neural network, right? So there's a group of companies, people who thought that's a good idea to just do that. If you do that, if you try to have this one big neural network that will do everything we want smart robots to do, what do you need to do then? Yeah, right. So a few problems with this approach. What you need to do, you need to train this large model. And then the model can be language model, it can be vision action language model, it can be any kind of foundational model or the world model. That's the latest, the latest greatest, it seems, for which people are ready to give billions and billions to train. So the problem with this approach is that large models require a lot of data. Right? So how do you get this data? You either build a little data generating farm, and you know there are some here, but there are some other places where these farms are at a different scale. Right? I have seen 100 people in one room training robots to collect the data, to do stuff. Or you can run a simulation. That sounds easier, but those of you who've done it know it's not really, and it's very costly, especially if the simulation is supposed to be precise. So there are a couple problems, fundamental problems with this approach. The first one, the world is really complex, and it's complex on different scales, right? For some tasks, you need really very fine scale. For others, you need a lot of things. And this complexity is immense, so at the very best, this approach will be very, very costly. So costly that only one of those 5 to 7 companies listed above are capable to have control over these models, train them. Even if we manage to train those models, the second problem comes. The world is dynamic. Things change, new things appear. You know, we have new products, new packaging for products, new processes. And the thing is that we want it to stay that way, right? We don't want to freeze our world and keep everything the same so that the models work well, right? So that's the second problem. We'll have to retrain them again and again. Remember, we want these robots to not just replace people completely. Why? Because there are some jobs where you cannot put people away, like in a hospital, right, or in a care facility. People will be there, and they need to interact with them. And interaction needs fast reaction. However, low latency is not something these models boast with, right? Either if they run local, they're still not real-time latency. If they run on a server, forget it. And another thing, like commercially, right? I think no one wants a one-size-fits-all robotic assistant. Like that assistant that I buy for my home, I want it to learn my routine, like what I do, my favorite things, but I don't want to share it with anyone. And also don't care what my neighbor's routine is. So I think robotics there is slightly different than writing emails, right? Or making summary of boring text that I'm just too lazy to read. Okay, now let's differentiate, because the size matters both ways. So some people say you need the bigger and larger models, and because the smaller one works worse, but the smaller ones are better in some ways, right? And this, I guess, you know it. So there's a class of models which I call neural networks that don't require millions of dollars to train, like the more reasonable ones. And those are, of course, behind all the robotic applications that actually do something useful, and I am pretty sure a couple of you have came in touch with such applications, where you can train a relatively manageable neural network to do some part of the task. The remaining problem here, however, is that usually this task will be relatively simple. So like keeping your body away from falling and moving forward is simple in the sense that at least your output is in the same modality. It's all about moving. And the inputs, you can also integrate them like more or less in the same cost function, which you can use to train your small neural network. We can enable interaction with a relatively static environment, so not too dynamic. And the question remains, how do you scale to humanoids and complex behaviors? And there, again, like you probably go to big models. So it seems that as a community, we're a little bit like in front of this wall where you have these big shiny letters, LLM or some large models is what we need to do. And then there's no other way than to just continue going in this direction. And people believe that because they invest millions and billions to continue going and break the wall, right? But it's maybe interesting to start steering towards neuromorphic computing to ask a question, how did we get to this place? How did we get locked in on this one single approach? So what I mean by one single approach is one algorithm, basically linear algebra on steroids, right? That's what all neural networks today are. Training, replacing any adaptive systems, any real learning. So it's all about training, gradient descent, like the simplest optimization method out there, maybe with a little bit flavors. And then also concerns for the safety, stability, interpretability, trust. security, like you send your data somewhere in some server, it would be used for training something. We just don't care. We just don't think about that. Yeah, we don't think about that, and all will be fine. So how did we get there? Brief primer on the history of computing, like a 3-minute primer. I guess you guys probably know it very well. So how did computing history go? So at some point, Alan Turing proposed this universal computing machine. Right? He said, hey guys, look, mathematically I can prove with this machine you can compute anything computable. And then a bunch of other people, in particular John von Neumann, they came up with the practical computer architecture. So he said, yeah, look, we can have, instead of this band that the Turing had, we can have a memory unit, and then we have a computing unit, and we can actually build such a machine. And then, the machine was built, the computer was built, and the rest of the story can be captured in one word. Any guesses? What's the word? Scaling. Right? Then we just had more of this. We went from, these bulbs to transistors, and transistors we could shrink them, and we followed the beautiful curve of the Moore's law. The computers got more and more powerful until it was not enough for one very important, or at least very lucrative application, which I guess everyone in this room also knows. Yeah, so for gaming you need to where do I have it? I don't have the phrase. Yeah, but you had to render images very quickly on the screen with some 3D geometry in them in real time. And the CPU was not good enough. So that von Neumann architecture was good for everything else, but it was not good enough to render images on the screen fast enough. And this is when the revolution happened, and some companies suggested another computer architecture, slightly different, more parallel, called GPU, graphical processing units. That's what allowed computer games to run in real time. NVIDIA in particular did a smart move, and they open sourced their software for programming GPUs a little bit, so that you could not only render images on the screen, but do other stuff. And then creative people came, hey, we have these neural networks. By the way, they were developed for processing images, those first neural networks. First for handwritten digits on envelopes for post, then for face recognition, it was important, then for traffic sign recognition. So it was all about images. So I would claim that all those main limitations of today AI, they are rooted in its history in computer vision. I know computer vision, processing images, comes from 200 years ago when the first camera was introduced, supported by the GPU. So that's why it's slow, because latency was not really optimized for computer vision. For computer vision, I need to analyze an image. I don't need to do it with a millisecond time. The millisecond time frame, because it's not a control problem where I have to balance something that otherwise will fall down. Latency is not something which was optimized there on any level, like system, sensor. Even sensor itself is already too slow, 30 frames per second. It's not efficient because you have this redundant, wasteful representation. I'll show you the alternative in the next slide, and then we can dive into there. And this one algorithm for all tasks and training instead of learning. So other alternatives, and that some of you know already. Okay, so let's focus on vision, right? Can we do vision differently than with the camera that makes images? Can we think of that? It's interesting that we cannot, out of our head think of that, but we do that all the time. So our own eyes are not sending images to the brain. That, I hope, is clear for everyone. There's no clock that samples 30 times per second. Okay, guys, what's happening? You can imagine that eyes works differently, and somehow there's one patent out there that decided to build a chip that also does it differently, like the eye does. And that's the dynamic vision sensor, event-based camera. That's the typical output of this camera, observing a coin rotating in 360 rotations per minute, very quickly. So what you do there, each pixel detects luminance change, brightness change, with something called brighter or darker. And if this brightness passes some threshold, it sends an event to the computer. So if I observe a static, all very static, for instance, if I observe this scene, nothing moves, normal camera will send 30 times per second to the computer, million of pixels. Okay, look, did something happen? And this camera will send nothing, most of the pixels, and if something changes, like someone nods, those pixels will report the change, but very, very quickly, with a millisecond time delay. Yeah, so my colleagues from the sensors group of Institute of Neuroinformatics have a very nice video of that, which you can probably find on the internet as well. Right, so it shows kind of the snapshots of a disk connected to a drill. It's rotating with different speeds and shows what the normal camera does, the snapshots. And below is what the event-based camera is. So no new events if the disk is static, and when it starts moving, then you get the events. If the disk moves very, very quickly, then you get motion blur in the normal camera. 30 milliseconds is too much if the scene is static. If something moving very quickly, then it's too slow. But in the event-based camera, you have this continuous stream of events from the changing pixels. Okay, so look, we can do it differently. It requires another hardware. It took 30 years to put it in the market, and there's only one design for some reason. But still, it's possible to do things differently. Okay, so you could say, okay, we don't have fast vision sensor. Nice. Can we still do what the other people are doing, just normal AI? So much easier, 5 lines of code, TensorFlow, and it all works. And this is, of course, what a lot of people do. The sensor has been around for a while. Most people take these events, collapse them into frames, and then do the normal AI. But you can imagine that to really take all these advantages in terms of power consumption that you need to compute, in terms of the speed, it would be good to do it differently, to do it in the same way like this sensor is doing, this asynchronous, event-driven way. However, do we even have a choice? Because if I now go and shopping for the hardware that I could use to process that output, I basically have 2 choices. If I don't want to program FPGAs or do something very exotic, it's either a CPU, but the CPU, the problem is it's sequential, right? But I still have a lot of events, right, that I need to process, maybe millions per second. So the CPU will potentially be too slow. I could use a GPU, it's parallel, great, but it's a different type of parallelism than what I need. Like, I don't need to produce images. I don't have this, stacks and vectors densely filled for which GPU was optimized. It was optimized to put images on my screen, not to process this, asynchronous information. And there's basically nothing else. There was nothing else. Okay, so, neural networks is kind of a very inspiring concept, right? And we know that neural networks actually can do much better than those very static networks that you train once and then use for the rest of your life. And the examples of that are biological brains. And you don't have to think about only our brain. Like, a fruit fly. Where's my fruit fly? Let's see if it's running. Has some sophisticated behaviors. Its whole nervous system has 100,000 neurons. Right, that it can fly around, it could go to nice smells, away from bad smells, can mate, can do control, crawling, flying, all kind of behaviors with only 100,000 neurons. It's less than 1 layer of a very modest CNN. Right, and then if you go to bigger brains, like little birds with 1 million neurons, can do even more amazing things, can learn new things, and then you get the human with 100 billion neurons, which is still almost nothing, right, compared to large language model, and can do all that amazing thing. And they're adaptive, flexible, they can learn very quickly. You can show a thing once and then it will get it. Can be very precise, even though the biological kind of signals are noisy, and is extremely efficient. Our whole brain consumes 20 watt of power, less than Jetson. Okay. So there's a field of this bio-inspired robotics that has been trying to do that, trying to get inspired by biological structures in different brains and develop robotic algorithms out of them. I have a couple examples. One is from Guido de Kroon at the Technical University in Delft. He works with these very lightweight drones. The whole drone is coupled drum, so you cannot put a Jetson on it, but you want to control its flight. And he builds vision-driven control for those drones inspired by the algorithm that bees use when they land. They look at the optical flow in some sensor and look at the divergence of this optical flow and try to keep it constant. And when they do that, they control the speed of their landing and keep it constant. Yeah, so he has shown how you can have a very small system, very small neural network that can do that. Another group in the UK, Barbara Webb, she studies ants, and ants, particularly in the desert, have some very cool abilities. In the desert, there's not too many features to track, but these ants can go a kilometer away and then come back to their nest. Small brains, as you can imagine. And there are different things involved there. They have some polarization, light sensing, but they also have a particular type of odometry that they use when they do that. And this group has implemented this odometry mechanism, and they actually sell it. They have a startup, and they sell it as a very lightweight odometry software for AMRs, autonomous mobile robots. And the oldest, maybe the most famous example is from Michael Milford. It's called RedSlam. So it's simultaneous localization and mapping, inspired by some networks in the rat's brain. And those networks, they're famous for place cells and grid cells. These are some cells, there was a Nobel Prize for them, that seems to keep track of the position of the rat in its hippocampus and entorhinal cortex. And the structure in those networks is very well known by now, because people could study it with some fluorescent microscopy and such. So there are some, over decades, there were these point successes. We've understood some algorithm, we've implemented it, the results are not bad for the robot. But could we put it all together in some kind of a theory of brain-inspired compute, 2.0, because of course 1.0 is the LLMs probably. So how the brain computes? What do we know about that? We know a few things, but the core elements. The first are the building blocks. So the building blocks are, of course, the neurons. However, those biological neurons, they are different from the neurons that we know from GPU-based neural networks. They are event-driven and stateful. They're a little bit like those pixels in the event-based camera. And they also have a state. So usually in your neural network, input comes, and then the neurons, they're just functions, right? They apply the sigmoid function and then pass the value further, and then their internal state is reset for every new input. But these neurons keep a state. So they are every input puts them in some state, and then the new input already arrives at that state. State space models go a little bit in that direction. Brain have different neurons, so it's not just one type of neurons. There's 100 of different types of neurons. They are all stateful, they all have some dynamics, so some temporal kind of evolution, and many of them are spiking. So some people believe all useful neurons are spiking, so they generate events. In reality, not all of them are spiking. Yeah. So instead of this function of a neuron that is in the normal artificial neural networks, what neurons are doing, they generate events, they receive events, and internally they have this variable that has some dynamics, which you can use for computation. Okay, and the second element in the story are the synapses. So instead of weights, you have these connections, they're called synapses, and they have weights, so the strength, but they also have delays introduced to the system, which again is another computational block that first allows you plasticity, and plasticity is this learning that is the actual learning, that your structure of your system can change on the fly. It's not trained once by open AI for billions and billions, and then you have to use it. But actually, the structure, the weights are changing all the time, and that's what happens in our head, of course. So your variables are not only neuron states, but also the states of the weights. And then there are some other parameters. There are delays, and there are some tags. So some input can tag a synapse, ready for update, and then when another signal comes, dopamine, and there was a good idea to do that, then this synapse is updated, but not the other. You can have some traces, in shunting, so there could be one signal that allows a connection between two other neurons. So it's the whole computational language, which goes far beyond what just normal linear algebra of today's deep networks offers you. And then branching is that the neurons have these more complex tree-like structures. So you can have multiple synapses coming to a little branch, some computations happening here, and then it's fused with some other branches, and single neuron can actually do quite a sophisticated computation. Yeah, but these two guys is all you have. This is one thing. Okay, so that's kind of the basic of what is called neuromorphic computing. There's not only that. So in the brain, you can go one level up and look in different circuits that are out there in the brain. And surprise, surprise, they are not just all these deep learning, convolutional or transformer architectures, as you can imagine. There's one fun fact in our visual system. That's the one that the deep learning models. The connections that go from your eye, up the hierarchy. You have this hierarchy, you have V1, simple features, and you have more complex features, and then at some point you have your grandmother neuron that tells you, oh, that's my grandmother in front of me. Okay? So what's the percentage of connections that goes in this direction? What do you think? I'll give you a baseline. For deep learning, it's 100%. All connections go from my input to my output.
5 to 10.
Exactly. 5 to 10%. All the other connections, they either go in the opposite direction, kind of priming me to see my grandmother when I entered her room, or left and right, just stabilizing some stuff on the way, some decisions maybe on the way. So you can imagine how different that architecture is. Okay, so I have 4 my favorite facts about this circuit level computation. So first, the cortex, this is the part of the brain that makes us so smart, seems to have these several layers, all across species, all across our cortex. We have 6 layers. And they have more or less canonical connections between them, between these layers. And it's the same in V1, V2, IT, and auditory cortex. And these circuits seem to do something like consistency check. So they're constantly checking, like, did what I thought will happen, did it happen? And if it didn't happen, that's a signal, locally generated signal to update something, to learn, to change something. That's kind of the basis for continual learning and adaptation. Then, when we think about brain, we think a lot about the cortex, forgetting that there are a lot of structures down there in the brain, which is also very important. And one of those important structures is thalamus. Thalamus is like a relay. It's a deep brain structure. All the sensory inputs, they go to thalamus first. Visual, auditory, from the skin, from motor sense. And then the thalamus connects to the rest of the cortex, gets connections back from the cortex, and creates these thalamocortical loops, which kind of compete for what's the important stuff I should attend to next, I should engage in. Because you can imagine the brain potential could be bombarded all the time by all kinds of inputs, like what my skin is doing, what my leg is feeling, and the thalamus makes sure that the important stuff is it goes into a resonance, is highlighted, and the rest just stays below our consciousness. Okay, and then we also have basal ganglia, cortical basal ganglia. The basal ganglia is this funny structure inside the brain, which is responsible for orchestration of kind of discrete behaviors. You know, when I decide to make a step, I decide to grasp something, there are these discrete behaviors. And what basal ganglia seems to be doing, it inhibits like a lot of the cortex, and then if I engage in some behavior, it disinhibits. So I want to say something, okay, this talking thing is disinhibited. So it kind of orchestrates what you are doing. And again, it forms loops with this thalamus. Cerebellum is this part of the brain down there, like somewhere here, controlling our movement, kind of. It has as many neurons as the rest of the brain, 80 billion. They are very small, so they're very hard to study. So we don't have too much of an idea what exactly they're doing. But they form some structures that seem to be involved in adaptive learnable mappings, and do muscle coordination and also movement fine-tuning. Must be quite important. And then there are those hippocampus and the terminal cortex. Remember rat slam, like those navigation circuits in the rat. They're also very well studied. And like you can see how they do odometry, form kind of a map of their environment. But also the same region is responsible for maps of environments, but also for episodic memory. So it kind of maps in time. Yeah, so what we can see is that in the brain we have many different algorithms, not just one. And also continual learning and adaptation. So all these connections, or many of these connections, are plastic and changing. So it's a teeny tiny bit more complex. So why? GPU is a great piece of hardware. It's parallel. It's great. I could maybe run it, but why is it not a good match for this type of algorithms? It's parallel. So my architecture is also parallel, but it's not exactly images. It's not these dense matrices of numbers. Full rank tensors. They are sparse neural networks, more like graphs. And a lot of them are recurrent with loops. And it's not something that this whole paradigm of image processing likes to. In image processing, there are no loops. You have an image, you have to analyze it. There's input and output. There's no loop in there. So the whole kind of pipeline is not developed for that. Different transfer functions. So it's not just rectifier linear unit. You have stateful neural networks. You need some local memory to have a stateful neural network. So your neural network is not just a function. What is a GPU? A GPU is multiple processes, same kind of multiple data, same process. So you have a little function, and then it's applied to different data. But here, you need some memory. So it's not just a function that you implement there. So you need some local memory, not just memory somewhere outside of your processor. And moreover, your weights can change on the fly. So you need even more local memory. And then you need asynchronous processing, because in these networks, the computation is not clocked. Like, your brain, some part needs to be fast, some other part doesn't need to be fast, and then it also is not running at gigahertz clock somewhere. You have different sampling rates. Okay, so luckily, some time ago, people started to explore. They started exploring a bit bottom up. They just said, can we build a hardware that is a little bit more like a brain, like the brain? So they started building these neuromorphic chips. In the beginning, they were not very practical. I think in this lab you maybe know about building biologically inspired things. They're not obligatory very practical, because they were just trying to better even understand what biology is doing. But over time, they became more practical, and now I think we can distill their key characteristics. And that they offer parallel compute, but it's not for dense matrices, it's for sparse graphs. It's asynchronous, event-based, the spikes or events. It doesn't have a clock. And they can learn on the fly through local learning rules. So you have this local memory that allows you to keep the states of the neurons and also the state of the weights, and then have some update rules for them. Yeah, so it's like a new hardware architecture, multiple architectures for next generation AI, or one of next generation AIs. I'm all for having like different things, not just one thing. People say it's better for control. These are different examples of neuromorphic chips. I think I'll go through them in a little bit more detail, but first, like the slide, at Intel, they also had a neuromorphic chip like that, and for that chip, they just have shown how much more efficient can it be. So they have this little plot where they show the energy ratio, so how much more energy efficient their chip was compared to some other chips, and the solution time, how much faster it was. And you can see it's 5 orders of magnitude more energy efficient and 3 orders of magnitude faster, just in practical terms. Okay, what kind of neuromorphic chips are out there? Costly can be divided into like really crazy ones, and those are the mixed signal analog chips. So you can build this neuromorphic technology using some analog circuits, so like below digital, and that's of course very ultra low power, but has some limitations on how big they can be, how many neurons you can implement like that. And then there are digital ones, like from Intel Labs doesn't exist anymore, but the Neuromorphic Computing Group that still exists and continues developing next generation of chips. Yeah, so and this is how the chip would look in the inside. There are multiple cores, each has some memory and a little processor, and then they're interconnected in such a way that they can communicate with each other efficiently. Okay, so when I entered this field, there were these chips out there, and then the big question was like, okay, we have the chips, we build them. They were building them inspired by the brain structure. How can we program them? Like, let's now do something with them. And of course, one thing that now a lot of people do, okay, let's not just do deep learning with them. And you can do that, and some people really fight to show that you can be more efficient and fast. But can you build other algorithms for them? Okay, now let me maybe look at our time a little bit and also how tired you are. Yeah, so I'll start like historically. So one thing, what we started doing when we had those chips is building simple algorithms that could fit on a very small and simple analog chip. It had 256 neurons, 256, right? You can almost count them with one hand. And also all connections. And we want to do something robotic with them. So we did the simplest possible thing, the Breitenberg vehicle. I assume some of you maybe know Breitenberg vehicle. If not, Google. There's a little book. It's a really fun thing. But what it does is reactive navigation, avoiding obstacle avoidance, going to targets, based on what you see at the moment. So we've developed this little neural architecture. So it's like the algorithm. How do I express this algorithm? There are two ways. Either I draw a picture like this, where each little white dot is a neuron. So there are literally 256 neurons there, and then I group them so that you can see which one of them is doing. And then there are connections. They can be positive or negative, red and blue, and stronger or weaker. On that chip, I could choose one of 4 weights for positive and negative. So really super, super simple. And then I have obstacle avoidance part and target acquisition part. Allow me not to go into detail. But the result, I could have this little vehicle that could drive around an arena. It had a little event-based camera, and if it sees something, it would go around it, and it had some concept of a target, blinking LED, it would follow it. Yeah, another example of simple algorithm, sequence learning. So, imagine you have this bag of neurons, spiking neurons, and you want to learn a sequence with them. So you have 256, not 256 million, right? So how do you do that? So there's an architecture, like a circuit that allows you to store sequences. Basically, it has some neurons that represent the position in the sequence, first, second, third. And then you have like the content of your, like whatever item is, some actions. And then you just learn the connections. The first one should be connected with this action, the second one with that action. And you learn these vertical lines are the learned connections. And you can teach the system the sequence, and then it can kind of replay it. And again, this is another way how I can express such an algorithm. It's the connectivity matrix between 256 neurons, where the blue ones are negative connections, the red ones are positive connections, and that's my algorithm. I put it on this analog chip, and it allows the little robot, to learn some sequence of positions. And like one robot shows the other robot, that's the sequence, and then the first one repeats. Very simple, very sandbox, analog chip and such. We have some work where we were scaling up this sequence representing architectures to more complex behaviors. We learned them with reinforcement learning. We did some planning on them. I will not go into detail. I'll briefly show you like more things you can do with that PID controller. when I have one measurement, I have the measurement that I want to have. I need to subtract the two. That's my proportional signal. I want to drive my motors with that. Now, if I have my 100 neurons to represent a value, how do I subtract two values represented there? And without going into detail, there's a little circuit that does that subtracts two values represented with positional encoding. Like when I have 100 neurons, and then if the second one is active, that's the value number 2, and then here I have the fourth one active, that's the value number 4, and I would subtract this from this. So I can have a little circuit that will give me as an answer, if it's 4 and 2, then the second one active. If it will be 5 and 2, then the third one active. That's this little structure there. I can go into detail. If you want, it's called gain fields. People actually found such neural structures in the brains of animals. Okay, so that was the P controller. You can also do the PID controller, We've implemented it, run it on a little rotor. And so the interesting thing is like when benchmark it, then we could show that even with the vision of course implemented with the fast event-based camera, we could have less than 200 microseconds update rate with the vision in the loop, and run the controller at 20 kilohertz with vision in the loop. Okay, so we were playing around with that for many years, and you can also do some vision tasks like depth perception and. So the conclusion of that it looks like we can build neural networks that are not just perceptron. Perceptron is like if it's convolutional or transformer, it's always input, output, many layers to train it with backprop. Interestingly, this concept of the perceptron, was introduced by Rosenblatt in his book, 1962. I don't know how many of you read it. Very fun read, actually. I looked through it recently, really fun. So that's the structure of the perceptron that he suggested, and it basically inspires the whole field of AI today. Like if you read this book beyond page 5, you see that he also looked at other structures. And he actually suggested that the neural system should look more like this. Like this is the muscles and blunts, and that's their external environment, some sensor modules. And many of the errors, they go like not just in one direction, but also in the other direction. This is one thing. And then another thing, it looks like we can build like different networks that correspond to all these different brain structures. Cortex, basal ganglia, thalamus, cerebellum, spinal cord, they're all like slightly different algorithms. Yeah, so it looks like we can build a new framework. I will now briefly highlight the important components that we can get. We can get learning back, namely continual learning. So we can have networks that can learn on the fly. And I wouldn't go in detail how. There are some papers from Elvin Hajizada who shows that, but to this network I can show it an object and say, okay, that's pink flamaster, I can say the Russian name or whatever, bloop, and then it will remember it and will try to recognize it. If next time it sees it like this, it will not recognize it and say, oh, by the way, it's still the same thing, and it will learn, oh, okay, this thing can look like this and can look like that. So it can learn things on the fly because it has the capacity for that with these plastic synapses. Yeah, so I think putting back continual learning is important. Second thing that is important, that today's machine learning assumes that a lot of computing, useful computing, is pattern recognition. Right? So image processing is pattern recognition. Now I give you some text, you give me the next word. You recognize the meaning of these patch of text, you give me the next word. Or it's always some input, some output. And then some mapping, some pattern recognition. I think a lot of computing is rather like SLAM, simultaneous localization and mapping. I'll show you little neuromorphic networks for that. But important are just a step, so it's state estimation. Where am I now? If it's literally about moving around, then it will be my orientation and where I am in 2D space. It could also be understood more abstractly. What's the state of my system now? Map formation is useful so that, for instance, my eyes are moving around. Right, so I recognize something there and then I look away. So it's good if I still kind of remember what I've seen between my saccades. So map formation is important. Place recognition, if I come back to the place, it's good if I know, oh, that's the place where I have visited 5 saccades ago. Everything is still the same there, by the way. So this place recognition is important. And then if I discover, oh, something changed, it's good that I can detect that something has changed. So this error detection. And then do something about that. Learn something, change something. Maybe update my map. Maybe update how I do my state estimation, my odometry. Right? So I think like this recipe for computing is much more useful, much more relevant than just pattern recognition. Pattern recognition is just too small of a thing. Okay, and then kind of the final step is that, yes, we have all these different algorithms, and because they speak on the elementary level the same language of those neurons and those connections between them, maybe spikes, maybe just values, I can connect them all together, like they are connected in the end in our brains. Yeah, and in this way we can build this new AI. Now I have a very kind of simplified sketch of that, right? So these are neural networks, but they're not image-like. They're not just matrices and they do matrix multiplication. They are heterogeneous neural algorithms, so I have different circuits, very different ones. How do I know what circuits are out there? Now I can either just be creative. People have come up with a thick book like this of C++ algorithms, right? We can come up with algorithms here, or we can get inspired by biology, because a lot of circuits, biology came up with amazing stuff. It has continual learning built in. And it allows for both fast updates, so fast learning, and also fast reaction, because I can have different time scales in there. Yeah, so we are trying to like build a system like that in 1.5 startups that we have. Yeah. Okay, so take-home messages. The first one from the application, we need more automation. So some people say, oh, we're so worried. And how will... Yesterday I gave this talk at the Zürich airport and someone asked, how do you imagine the Switzerland will look like if all those robots automation happens? And I'm like, from us from the outside, probably nothing will change. Because a lot of that work that you want to automate is not visible anyway. Like, if you're in a hospital canteen, someone is sitting and, how do you call it? Like carrots, peeling the carrots. Because there's no machine, there's machine to peel potatoes, but not to peel carrots, so people are doing that. There's a lot of work that is being done in the undergrounds of our society, and more of this work will be automated. We might not even notice, right, if it's done in the right way. I believe that today's AI is not enough, and I know I'm not in the mainstream on that. There are some reasons for that. I think the cost is too high. I think even if we manage no fast learning, it's still not so good, and this one-size-fits-all is not good in robotics. It's maybe okay in other places, but I think in robotics, especially if robots are supposed to be in our homes, we need more personalization. But I think this new neuro AI is upcoming. Like on one hand side, it will enable this fast real-time vision for control. Vision usually is not used for control, but when we are moving around, we do use vision. Like, if I close my eyes, one can show that even my posture control gets more shaky. If I run down the stairs, I'm not looking at the stairs and recognizing every stair, but I don't want to do that with my eyes closed. Like, why not? I saw the stairs, just run. Yeah, but you don't do it with a camera-like sensor. You do it with this different sensor. It will be more safe and efficient, and fast learning will allow for this personalization and privacy. I don't need to send my data to the server and hope that someone will do something good with it and give me back my product that I need. Yeah, so I'm happy to connect. I'm happy to answer questions. We have bachelor, master thesis works. We have 2 startups you can join and support. Yes, happy to stay in touch.
So I remember, like, during my bachelor's, I took like a course on like how neurons work in the brain, and then I guess I was trying to apply it to robotics, but I realized that most of the stuff there was very either like very abstract or like very specific to like what they found out, that it's very hard to apply it to robotics. And I was wondering how you kind of try to take insights from neurology and find ways to make it useful in robotics.
Mm-hmm. I think the trick is to know both worlds. To know these algorithms in robotics, to see kind of the abstract patterns from the neuroscience. Because yes, if you work with computational neuroscience, they do get lost in details, and the experimental neuroscientists even more, understandably so. But that's this this step of abstraction. I think it's important to know what you want to achieve. You want some robotic algorithm, you imagine what are the building blocks, and then you can get inspired by the neuroscience.
You mentioned a few times that the brain is not clocked, but I think you're overlooking that it has emergent clocks. Like, it has these gamma oscillations, alpha oscillations, and so on. Mm-hmm. Especially with the rats and the place cells and the grid cells, they have shown that when they fire relative to the oscillation matters. So that encodes information like where they are within the cell.
Yeah.
So aren't you missing something if you don't consider that there might be some clocking going on and things have to be synchronized maybe?
Yeah. So first, these clocks, a lot of them are like local, and then they could be kind of emergent behavior. I think it's very controversial in neuroscience whether they have functional role. So they could be, it's not that the clock is there and then where your spike is relative to the clock plays the role, it's kind of the other way around. The spikes are where they're needed for behavior, by the way, some repetitive behavior when they run around. And because of the arrangement of the spikes, like this rhythm emerges right there, but it's not that the rhythm is functional. So the rhythms, they are controversial, their role in the brain processing. Yeah. Because they're kind of there, but they're too generic to really be correlated to all kinds of behaviors that people engage in. And there are some rhythmic behaviors, but there are a lot of not rhythmic behaviors. Kind of imagine piano player can play all kind of rhythms, all kind of stuff, and different. Like how do you correlate it with like 4 rhythms that you see in the brain? Like, yeah. So for some behaviors, like for some animals, they could be, but it's not like everyone is there sitting with a clock.
Well, I mean, I think for example, walking, it's not controversial. Like, there is some kind of rhythm generator for when the fruit fly walks, for example, how it.
Yeah, but it can work with different speeds.
Sorry?
It can walk with different speeds, very different
That's
rhythms.
true, but you can tweak an oscillator's frequency.
Yeah, but this alpha rhythm is always the same range at least, right? So beta rhythm or whatever. There are oscillators in the spinal cord. That's true. So there are oscillators in the spinal cord, and there are some theories that these oscillatory behaviors are primary. So all our movement is generated with oscillator in a way. It's just for some movement we learn to stop this oscillator on time, to do these discrete movements. Like when I do my reaching movement, it's not an oscillation, but the basis, like the generator, is actually an oscillator. I just stop it halfway, and I learn to stop it halfway. But that's in the spinal cord.
So for I guess the neuromorphic chip, I guess like it's very similar to the MCU. But if I assume that this neuromorphic chip parameters also updates like the MCU, then I guess online training is quite very difficult, I guess. So is it possible to do the training in online and continuously update the parameters?
So because you don't do it for your whole system, so the whole framing is different. It's not that I have my bag of neurons, I have input and output, and now I kind of train it online. I can do that, but there are other challenges with that. It's more that I have this circuit, it has different structures. In one structure, the weights can be updated depending on the dynamics, on the behavior of the neurons. And usually in biology, like these synapses connections, they depend on the state of the 2 neurons before and after. Like if this guy has fired, and then sometime later this guy has fired, the weight will go up. Otherwise they will go down. So these are kind of the rules, but these rules can be more complicated than that. So it's like a dynamics that follows some rules, and usually you need some dopaminergic signal, so like some punishment or reward, and then some weights will be updated that were tagged beforehand. Right? And in order to do that, you need some local circuit that will just keep the state of this weight and then update it if something happens. And you do that to really learn something new, like, oh wow, there's a new object, what's that? Then I learn it. I don't have to learn most of the time. There are some people who claim there's very, very little learning actually happening in life. So they show even like for larvae fish, like they are little fish, they grow, but there's very little learning. And a lot of the learning might be like developmental programs unfolding. Like we really underestimate all this whole DNA encoded developmental stuff. You know, when I look at our body, like when my hand has formed like that, a lot of my brain has also formed following this developmental program from DNA. So to assume that the brain when you're born is just this bag of neurons and then it's all trained, learned by behavior, by experience, pretty naive. There are some animals, they are born and they can run right away. How many of you are from the village, right? So that's one thing to keep into account. There's a lot of structure there, and then just a little bit of learning in a kind of somewhat controlled fashion with a lot of parameters there.
I wanted to ask, to continue on this question. Basically, the structure and the chip that you showed and the algorithms that you apply to it, these algorithms are like fixed, and then there is a little learning involved, or can the chip like learn on its own an algorithm, or how does it exactly work? Like, how much learning is there involved, and can it be like open-ended in some ways?
Depends on the chip, and there are a lot of chips now built by different startups who try to ride the wave of deep learning, right? And people, of course, look for systems that would make large language models more efficient, and a lot of that more efficient during inference. And there, of course, you don't need any learning. So, for instance, part of the neuromorphic field is in-memory computing, and that usually doesn't have learning in that sense. Now, you have some network, you just put the weights, and then you can run it very efficiently, maybe optimized for sparsity. So I worked with two chips that have this learning of parameters. One of them was analog. So people came up with a little circuit. The weight is expressed in charge on the capacitor. And then there's a little circuit that defines when the charge is pumped in or out of this capacitor, depending on the activity of this neuron before and neuron after.
Okay.
So, ingenious engineering, but they managed to do that. The chip is analog, and analog has its own problems. It's very sensitive. You do this, all your neurons are suddenly like firing more heavily. And then the other one, or two even, Loihi, also had a learning engine. So Loihi is these processors. They have like 160 processors on a chip. Each one has a memory. So the memory holds the states of the neurons and states of the weights. And then there's one processor that updates the state of the neurons. They typically implement this leaky integrated fire dynamics. They integrate incoming inputs, and then the state leaks over time. Right, so input comes, it grows, maybe it reaches the threshold, and then the neuron spikes. Maybe it doesn't, and then it just decays over time. That's what neurons are doing. And then they also have another engine for learning. And that's a little like program that just watches out, has the neuron before the synapse spiked and the neuron after. If they did, then I update the weight. So it's like a little program, learning program. And then the third chip is Spinnaker. That's a European invention from Manchester and now in Dresden. They just have an ARM cores as their like simulators. And there you can run whatever you want. So you can run a little program for this that will update your weights.
Okay.
Yeah. And you can follow the biology or follow something else. Yeah. Okay.
It's a bit more in the same direction. Can you briefly explain how you can program these networks in these chips to do what you want them to do in a way that, because you mentioned that one of the benefits is plasticity, and maybe reinforcement learning you can apply. But the brain, mammals, we have the dopaminergic system, also inspires these algorithms, but this is the rewards are shaped by evolution. And we have rewards for food and so on.
For Fs.
Yeah. But how can you program, for example, I want this robot to do this task in the network?
Yeah, so that's like the program that you put in. So dopaminergic is relatively easy. I can determine, okay, this neuron will be my dopaminergic neuron. So if it fires, it will influence the connections, maybe in some group of neurons, maybe in all of them. So if this neuron fires, all weights are allowed to learn. And then what they learn will depend on the history of activity before. It will be a little bit like reinforcement learning. I have some eligibility traces. So, some behaviors were involved in some sequence of behaviors, and then by the end of it, I get a reward. So everyone involved gets a boost, gets a little learning update. The more recent ones, bigger boost. The less recent one, less of a boost. Right? The typical reinforcement discounting reward thing, if you like classical reinforcement learning. So I can easily do that. Now these drives, right, depending on my task, so what I want the robot to do, I just say, okay, you are now responsible for the drive. If your battery gets low, it's now we're going into behavior organization. So briefly I've shown you the sequence learning system, and then there was the development of that behavior organization. And that goes, you need some kind of a state machine that controls which behavior shall I engage in now. And that goes back to something like Brooks, subsumption architecture. Rodney Brooks is something you guys probably learned here, right? The classics of robotics. So he had this architecture of different modules. They're responsible for different behaviors. One of them could be go to the charger. And this behavior monitors my battery is getting lower. So if my battery is getting lower, I'm getting hungry. So this behavior has more chance to be active. And then it creates a little bubble where I have a big tendency to go to a charger and ignore all the other targets that I might have. And then if my target grasp this phone is active, that's maybe my mood, like I need some communication, right? And I engage in that behavior. Yeah, so you can assign neurons to have these roles of reward system or what behavior to engage in now.
Do you need some kind of reward generator
reward generator.
Perception signal.
Sure. Yes, so you can have some neuron, and it's responsible for the state of me getting reward. And when I decide like how do I make these networks do something useful, I need to know what I want them to do, right? I have some robot has these sensors, so it need based on these sensors detect certain states, right? So I need to develop some detectors for the states, and now state ABC should be connected to behavior, well, D, E, F, and then these behaviors I also have. Maybe I train them, right? So I can have some simple mappings here and there. And then I just design them. I play that evolutionary designer. I don't wait them to evolve themselves. Some people study evolutionary algorithms, that's valid as well. But if I know what I want, I can just program it. Maybe at some, hopefully not with vibe coding, because there are not too many examples in the data set.
I have two questions. Amazing talk, thank you very much. The first question I have is, when you think of the GPU architectures that are already extremely scaled in terms of just parallel computing size, and at least I'm peripherally aware of the simulations that you could run on those to at least partially simulate a neuromorphic chip. And now you look at the performance you could achieve with that versus, let's say, you get a natively designed inter-chip for this. How do they compare at the moment? And if you want to approach this problem from a pragmatic perspective, first of all, availability of the chip, cost potentially, and just simply to try out algorithms while trying to explore the training of these algorithms. What would you recommend, or how do you do it?
Yeah, so the availability of chips is of course a big problem, right?
Yeah.
So we ourselves in our lab, we simulate this stuff on a CPU or GPU at the moment, right?
Yeah.
And the GPU, depending on how deeply you can go in this GPU programming, you can implement these networks fairly efficiently. Because the chips are a bit exotic, so the hardware. We are looking towards a product, right? And for product, there's no chip that you can buy and be sure that you can buy it in a year. Yeah, although there are some companies here and there, they're moving. So in terms of maturity of the hardware, today we have to use what's out there. Maybe like there is some work that develop tools for FPGA. So they will run your network on an FPGA, but they give you tools that you don't have to mingle with that hardware level description. And then you can run them. Yeah.
And maybe, so the second part is, for which type of robotics problems have you already been able to sort of show a clear advantage of using the neuromorphic architecture? Particularly if you think of currents of either the locomotion problems, or you were showing the quadrupedal learning architectures where you run like a PPO or something.
Yeah.
Is it applicable to this already?
Yeah, so that was one example that maybe was the most interesting, because there's a way how you can implement certain optimization algorithms on these chips very efficiently. They sample kind of the space nicely. So we had a project together with RSL, I think, on running the MPC. That they run in an extremely optimized way. So they run this MPC problem for the animal robot in real time with 4 millisecond updates. On Loihi we could get the same update, but the power consumption was 1,000 times less.
Oh, okay.
Yeah, it's again, of course, like the Loihi was a prototype. It has an FPGA with that. And if you measure like the system performance right now, we're like barely there. But if you imagine the next step, when it's kind of optimized and it's a product, then you could have much lower power consumption.
That means for the moment that you're running on FPGA, the cost is obviously high, but you're planning to do ASIC specific development.
Yeah, that's already ASIC, but the ASIC needs an FPGA to connect to anything else. And you need to connect to the animal, you need to connect to the rest of the computer and such. Configure it, monitor what's happening, and so on. Yeah, that's one nice example. There are a few more.
What about computer vision problems? Would it make the same sense? Can you use this neuromorphic computing to improve on performance in some way? Or how does it look like for classical tasks? Like you mentioned character recognition, digits, and presentation tracking.
So what has been shown by Intel Group is for video processing, because in the video processing, like even you have a normal camera, you have this redundancy from frame to frame, right? So you can make use of the sparsity of your computing network, which will be more or less deep learning network, but just because of the structure of the chip, you can make better use of the sparsity because of the redundancy that you have from frame to frame. You don't have to recompute everything from frame to frame. So that has been shown. Intel has some work on that. For pure image recognition, I think it's a bit more tricky to show advantage.
To improve the efficiency of these videos, what kind of task is it, for example, in videos that you try to solve
I think they have,
and benchmark against?
they had something like YOLO type of tasks of segmentation. application video. Yeah, we usually then take the event-based camera for vision as well, because then you have advantages already on the sensor level, and then you can leverage those advantages better with this chip than with the others if you have the right interface, which took a while to develop.
And the performance of the benchmarks gets better.
With the DVS or with the neuromorphic chip with the normal video? With normal video, yes, in terms of if you take power efficiency into account, not just accuracy. Right. Accuracy, like, your networks are limited in range. You usually have limited precision of everything, right? So it's like integer precision and such. So accuracy is on par, already considered good. Maybe it will be like 2% worse, but then you have either faster or less power consumption.
Thank you.
Yes, thank you very much for the presentation. Could you please briefly explain what the current limitations of the technology? Because, like, if that was the solution for all our problems, we would already use it. But what are open questions in the field, so it's not widespread yet?
Yeah, a lot, right? Where do I start? So I think we haven't, the field hasn't found its gaming industry yet that will allow to finance development of this hardware technology where it should be. Because even Intel, you might think, oh, that's Intel, but that was Intel Labs, research organization of Intel, heavily underfunded organization, and within that organization, something like 30 people spread across the world developed the hardware, produced it, tested it, put it in the system, developed algorithm, compiler, everything. It's teeny tiny, it's like one drop of water on a hot stone. And the other groups are even worse funded because they are academic groups, you do some prototype. And for it to be kind of worth it, some industry needs to buy into it, right? And you need to really invest. And today is not 2002, when GPU came on board. It's very difficult to build a new product in this hardware field, because it's not just building a product. The whole the interface, everyone has already adjusted their tools, their pipelines to use certain hardware. If you replace the hardware, everyone has to adjust everything. The cost is much higher, so it's hard.
But what are the fundamental problems?
Fundamental problems. So today's neuromorphic hardware has committed to a certain model, which is different from the model to which this GPU-based network committed. It's a bit more sophisticated model, but I think it's still not quite the right model. So I've shown this slide how the neurons are, and I said there are different types of neurons in the brain, maybe 7 different types which are relevant, but all neurons on the neuromorphic chip are all the same. If you biology here, all neurons, at least on one core, are the same. It's the same equation that will be iterated. And they are this leaky, integrate, and fire model, which is a nice model. Is it the best model? Is it the most relevant model? Not so clear, at least not for all applications. So I think you need to be a bit more flexible with what each neuron is doing. And then they usually fix the connectivity structure, 4,000 weights per neuron. For some places it might be too much. I want to build this central pattern, generate a little oscillator, I need 2 synapses per neuron. And in other case, I need more than 4,000, maybe 10,000. So that's also this limitation. So they have kind of put in the hardware some structures which they believed are the right ones, and everyone just followed that pattern. So this field also has converged. Everyone now converged in one model.
So it's converged. There is no some alternative that on some task performs better and on the other task this performs better. There's just one.
So it's basically one thing. There's some parameters, right? You can do, but I think not enough. And again, the hardware, right? Every cycle takes half a year, right? So it's not so easy.
And also another question, maybe it was partially answered, about this motion, training. You collaborate for this RSL, for example. You said that your processor is much more efficient in terms of compute. But what about sample efficiency? Do we need more real world data, for example, for robot to move?
Yeah. So that case was MPC, model predictive control. It doesn't have learning in the loop. It's just the control. You have a model of your system, and again, it's just mechanical model, just the equations. And then the question is, how do you simulate these equations? You unfold them over time, and then you unfold it 100 times, and then you run your optimization algorithm, selecting the best trajectory. So it's an optimization algorithm. It's not a deep learning algorithm.
Okay, but then maybe not any other projects, was it shown how much data do we need for this type of computers to learn some behavior? compared to like classical approaches with gradient.
Yeah.
gradient
So that's
design?
kind of not about on the computer, because you could run the same backpropagation gradient descent algorithm on this computer. So it's more defined by your learning algorithm. For this continual learning task, the continual learning task is when the task is to learn new objects. So you constantly have new objects, you constantly have out of distribution data, you need to detect your out of distribution and you learn it. So there we have had some benchmarks, so we have shown that you need less data than other approaches that also do continual learning. Yeah. It's also the question with these benchmarks, right? Benchmarks, they force you in a certain way of thinking, in a certain way of tasks. It's a certain play field. If your advantages are somewhere else, then if you play on someone else's battlefield, right, you will always lose. But then is this something that is useful for me to solve, this benchmark? That's the question.
If I paid attention correctly, you mentioned that the part in the human brain that is responsible for motion already has a significantly higher amount of neurons compared to a mouse brain. What is this part then more capable of compared to a mouse? Because a mouse can also jump, it can swim, it can run, it can...
Yeah. So I think this very dexterous thing takes a lot of it.
Yeah.
Because the mouse has only very simple grasping movement, right? And we can deal with objects of different size, like different texture. So I think a lot of that is maybe dexterity. And then maybe it also took over some other things that are a little bit more. So this is something it holds something like inverse and forward models probably, but dynamic ones, right? And that could maybe be applied also to in some more abstract spaces. When you do some problem solving, you're also moving in some space, so it could took over some of those tasks. But I suspect a lot of that is about what we can do with our hand.
Would an octopus then have a very complicated... I think they have a completely
Spread,
different...
yeah. They almost don't have a central brain. I think it's all spread all over the place. Yeah, they're quite amazing.
There recently has been a lot of talk, and I don't know a lot about it, so maybe you can also explain it a bit more, about optical chips for basically doing light-speed computation in big MLPs or maybe even CNNs.
Yeah.
What is your opinion on those, and do those solve also the problem maybe even better, or is there still issues there?
Yeah. So that's an interesting field. I happen to know a little bit about that because my original studies were in physics and physical optics in particular, back in the years. And we had this department of integral optics, so they were studying optical computer. And in optics, you can have all the elements that you need to build a computer. You have equivalent of transistor and all the elements that you have on a chip. So you can have all the nonlinearities, elementary circuits, you can do them with optics. It will be faster, it will have more capacity, right? Because you can interfere these waves and so on and so forth. So the problem why it doesn't take off is somewhat similar, because then on the periphery, when you go from this optical domain into a normal electrical domain, you lose the advantages. And then you need to invest to develop the technology, but then the whole infrastructure will also need to change. So I think this is one of the problems with that. So that's why most of the applications are a bit of a niche applications. So where you have a light anyway, so some laser control thing or communication. So for communication, some processing close to your communication line might use some optical computing elements. And the rest is research, right? And research people have shown, yes, you can have neural networks, you can computation, but again, scaling up to commercial has some, resistance. Yeah.
So just quickly, if you came later, please go by to J1 for scanning the lady in case you're taking it for credit. Just don't forget about that.
I guess on the subject a little bit on limitations, but maybe more from a neuro perspective. So you spoke, a lot about getting inspired by the brain, and then from a neuroscientist perspective, I guess researchers are would argue maybe that they don't know anything really much about how the brain works, and then they're trying to map, for example, when I saw the fruit fly brain, they're mapping, right, all of the neuron connections and coming out with this. So I'm wondering what your perspective is on this, are there things that we're missing? What do you think we're missing to understand? Do you think we know enough to actually limit it? And then are we getting stuck kind of maybe in the same, stuck in one way of thinking about how the brain works and like from the neuroscientist perspective. Yeah.
So neuroscience is its own field with very complex history,
Yeah.
complex politics, and this whole dynamics, social dynamics of a research field. Today also a lot dominated, let's collect a lot of data, let's rebuild the brain of a fly, a cat, a mouse in Geneva. There's a big institute, the Blue Brain Institute, that is doing that. And there are other people who criticize that a lot, that you rebuild the static brain, what did you learn? Let's better learn the principles. We cannot say that we know nothing about the brain. Some people say we know nothing about the brain. That's not true. We know a lot, especially like particular circuits, particular systems, particular structures. We definitely don't know everything. And there's definitely a lot of these dogmas being building up. The neurons are very important. Now some people say, but there are also other cells like astrocytes, glia cells may also play some computational role, but this neural dogma has been dominated. And some other people say spikes are very important. It's all spiking. But then there are some animals, they have neurons and they're non-spiking. Those are difficult to look at because when the neuron spikes, you can see it. You can measure it, right? You can see it blinking. If it doesn't spike, I cannot measure it. So, if I cannot measure it, I just don't look at it, right? And ignore it. So there are always some dogmas, right? And then there's some strong personality and he makes this very dominant and then field gets stuck in that paradigm for a while. It's a complex field, but I think still it produces a lot of inspiring elements. And there are some people who try to give the whole thing a thought and try to put a lot of bits and pieces together in like one system. So I was citing this cortex and this thalamocortical loops, this basal ganglia. So there's one guy in Princeton who's trying to put like a lot of puzzle pieces together and have like a bigger picture. But the field I think is also somewhere around like alchemistry level of understanding of the subject matter. Doesn't mean that we cannot come to physics and chemistry. No, good understanding. Would be very useful for many fields. All right. Good.
Thank you very much.